So I'm pleased to welcome Julia Stawarz, who's today's speaker. Julia completed her PhD in 2016 at the University of Colorado in Boulder, after which she then joins the Space and Atmospheric Physics group at Imperial College London, where she still remains today. As of October of 2020, she became a Royal Society University Research Fellow. That's the position she holds currently. Her research focuses on using spacecraft observations to study space plasma turbulence, magnetic reconnection, and related small-scale plasma processes in Earth's magnetosphere and solar wind. And for that research, she was awarded in 2018 at AGU a young early career award for excellent research excellence. And also this year, she was awarded the Whittam Award for Geophysics from the RAS. So without further ado, I'll hand over to Julia, who will talk us through her latest research. Thanks.
Thank you, Greg, and thank you to Jasmine and I guess the whole MIST committee for inviting me to give a seminar. Thought I'd take the opportunity to wish everybody a happy beginning of LGBT Pride Month as well. So my name is Julia Stawarz from Imperial College London, and so I'm going to be talking to you today about turbulence and magnetic reconnection and what we've been kind of learning from the Magnetospheric Multiscale mission about the interaction between these two fundamental plasma processes. So just to outline my talk, so I'm going to begin by giving a bit of an overview of what turbulence actually is. Then I'll talk about kind of the various ways that turbulence and magnetic reconnection can interact, and some of the ways that we've been looking at that with MMS as well. And then I'll go into a bit more detail about some of my most recent work looking at kind of turbulence-driven magnetic reconnection in Earth's magnetosheath. So to start with, what is turbulence? So turbulence is the kind of complex, highly nonlinear behavior of fluid systems. It's found in systems throughout the universe, both in kind of neutral fluids, which we find here on Earth, like the Earth's oceans, as well as the Earth's atmosphere, as well as in the atmospheres of other planets. So there's these great images from Juno of the kind of complex fluctuations in Jupiter's cloud tops. And of course, turbulence also occurs in space and astrophysical plasmas, such as the solar corona and solar wind, as well as planetary magnetospheres, which we're all very familiar with here in the MIST community, as well as kind of more exotic astrophysical environments like the interstellar medium, black hole accretion disks, or even kind of galaxy clusters at some of the largest scales in the universe. And within these systems, turbulence plays a role in kind of creating the structure that we see in the universe, mixing together different fluids, as well as kind of scattering, accelerating, and heating the particles within the fluid. Within a turbulent system, the nonlinear interactions between fluctuations at different length scales in the plasma causes the transfer of energy between different length scales. Typically, this occurs in an average sense from large to small scales, but there are situations where you can get energy going from small to large scales. And we call this an energy cascade. So if you look at the distribution of energy within a fluctuation energy within a turbulent system, then you tend to find that there's a broadband distribution of energy as a function of scale. It tends to follow power laws. The slopes of these power laws are related to the kind of nature of the underlying nonlinear dynamics in the system. And in particular, it's related to the time scale associated with the energy transfer at different length scales. And so often in the study of turbulence, you'll see people talking about what the power law slope of the spectrum is. And the reason that people care about that is because you can link that to what the kind of leading order nonlinear dynamics are through theory. And so if you imagine a plasma system, if you're at large, as you transition from the large fluid MHD scales in the plasma, you typically expect there to be a change in the power loss slope. And this is at least partially related to the fact that the nature of the nonlinear interactions changes as you move from the large fluid scales into the smaller kinetic scale plasma physics. Once you get to the smallest scales in the system, then the energy and the fluctuations can be more easily dissipated. So one way to think about turbulence is that it's the way that the system kind of moves energy to a length scale where it can easily dissipate that energy, right? And so if the system were collisional, that dissipation would occur through things like viscosity or resistivity. However, in many space plasmas, the plasma is collisionless. And so one of the big open questions in kind of space plasma turbulence is how this energy is actually dissipated at the small scales. And there are a variety of different processes that can be responsible for that energy dissipation. So it could be associated with kind of resonances between the fluctuations and the particles. It could be associated with acceleration through electric fields that are formed in the plasma. It could be associated with instabilities. And it could also potentially be associated with magnetic reconnection occurring in the plasma. If we look in kind of, so that's kind of what turbulence looks like in Fourier space. If we look in kind of physical space, turbulent systems tend to consist of kind of this complex mess of different fluctuations and structures across a wide variety of different length scales. So this is just an example of a simulation of plasma turbulence that I worked on with Luca Franchi. And so you can see that there's all of these different complicated fluctuations across different length scales. While you might be able to just describe any one of these individual structures, the whole ensemble of these is very complex, which is kind of the challenge of studying turbulence, is trying to understand what the ensemble of all of these different structures is doing. And as well as the kind of transfer of energy between different length scales in the plasma, one of the other characteristic features of a turbulent system is that the gradients that are associated with those fluctuations tend to be non-uniformly distributed. And we call this intermittency. So one of the important gradients in the context of plasma turbulence is what is the current, right? And so if you look at the distribution of the current within a turbulent system, then you tend to find that you have kind of non-Gaussian statistics. So you have a higher probability than Gaussian of having very intense currents, as well as very weak currents, and then a reduced probability of intermediate currents, right? And so that corresponds to the fact that you tend to concentrate the current into very small scale and very intense structures within the turbulent system. And if you're a turbulence person, then you can look at the kind of nature of these non-Gaussian statistics, tells you some additional information about the nonlinear dynamics. But if you're not a turbulence person, then and you're interested, say, in how turbulence might play a role in magnetic reconnection, then I think the kind of one of the key takeaway points is that turbulence is particularly good at making small scale intense current sheets. And these can potentially be sites where energy dissipation can occur and where magnetic reconnection can occur. However, as we'll talk about a bit later, there's quite a complex relationship between turbulence and magnetic reconnection. And there's a number of different ways that they can interact with each other, both in terms of reconnection events occurring at these small scale current sheets, as well as kind of reconnection playing a role in driving the turbulent fluctuations themselves. So over the past several years, the Magnetospheric Multiscale mission has been providing an excellent data set for studying kind of these kinds of multi-scale plasma processes like magnetic reconnection and turbulence. And there's kind of several reasons that it's particularly good for studying these phenomena, one of which is that it's a multi-spacecraft mission. So it consists of 4 different spacecraft. They're flying in or they orbit in generally in a tetrahedral formation, similar to the cluster mission. But the difference here is that the tetrahedral formation is much smaller scale for the MMS mission, because it's particularly targeting the kind of very small scales, approaching the electron scales in the plasma. The other unique thing about the Magnetospheric Multiscale mission is that it has particularly high resolution particle measurements, 150 millisecond resolution for the ions and 30 millisecond resolution for the electrons. This allows you to look at the particle distributions at timescales that are consistent with the subproton and approaching electron scales within the plasma. It also has 3D electric field measurements, which can be quite good for looking at the small scale plasma physics. It's an Earth orbiting spacecraft that was launched in order to kind of target looking at magnetic reconnection in different regions of the Earth's magnetosphere. And as a result, it explores a number of different plasma environments in near Earth space. So as the Earth orbits the sun, the orbit kind of precesses around the Earth relative to the Sun-Earth line. And so over the course of the year, the spacecraft kind of traverses the kind of dayside magnetosheath and magnetopause, as well as the Earth's magnetotail. And all of these regions are known to be turbulent. And in fact, they turn out to be kind of good environments for looking at different aspects of the interplay between turbulence and magnetic reconnection. Right, so now I'm going to talk a bit about the different ways that turbulence and magnetic reconnection can interact, and give, I guess, a slightly biased kind of highlighting of some different ways that MMS has been used to look at some of these different ways that turbulence and magnetic reconnection interact. Right, so the interplay between turbulence and reconnection has been a topic of interest for quite some time, going back to the 80s and continuing on through to the present day. Right, and as I mentioned, right, one way that turbulence and magnetic reconnection can interact is that turbulence can actually create current sheets that reconnection can occur at. And so here's just an example of one study that was done back in 2009 by Sergio Servideo, looking at magnetic reconnection events within a turbulent simulation. In particular, they were looking at 2D MHD simulations. This is kind of the simplest configuration that you could do. And of course, in 2D, it's fairly straightforward to find where the magnetic reconnection events can occur. Right, because you can just look at the kind of topology of the magnetic potential and identify the topological X points. And what you end up finding is that you generate a wide variety you continually generate a variety of small scale current sheets that are able to reconnect. And if you look at the kind of size of those current sheets, they tend to be very thin, approaching, in the context of resistive MHD, they're at the kind of smallest allowable scales associated with the resistivity. But the length of those current sheets tends to be quite a bit longer, right? And it's associated with the typical size of the kind of twisted up magnetic field structures that you form within the turbulence. So the kind of picture of reconnection that you have going on is that the turbulence creates these twisted magnetic field structures, and at the interfaces of those, you can get magnetic reconnection. Right, and so the reason that we might care about this reconnection that's going on at these current sheets is that it can both contribute to the nonlinear dynamics that are occurring within the system. So as the magnetic field changes topology, it releases the stored magnetic energy and puts it into the particle motions. And so it can be a way of, you can think of it as one of the kind of nonlinear couplings between the magnetic field fluctuations in the particles. So the jets that are associated with the reconnection will end up feeding back into the turbulent fluctuations. And there's been a number of studies recently that have been looking at how if you have magnetic reconnection going on and that becomes kind of the dominant nonlinear dynamic at a particular scale, then how that would influence the power law spectra that you see. Turbulence can also potentially play a role in facilitating the energy dissipation in the system. So this could either occur through the acceleration of particles in the vicinity of the reconnection X line, but it could also occur through kind of secondary processes that occur kind of in the reconnection outflows that are enabled by magnetic reconnection going on. It's not entirely clear to what extent reconnection contributes to that heating, or what fraction of the kind of turbulent dissipation might be associated with turbulent reconnection. Right. No, and I guess I forgot to mention, so the kind of typical, we mentioned that the reconnection occurs at these twisted magnetic field structures. And so in the context of turbulence, you can quantify the average size of these twisted magnetic field structures by what we call the magnetic correlation length. Right. And so, of course, this is all in the context of 2D MHD. So if you generalize this to 3D, things become much more complicated because you can end up with much more complicated magnetic structures. There's been some recent work by Jefferson at MSL looking at how you might be able to identify magnetic reconnection events within kind of a 3D turbulent context. But it's very much a non-trivial problem because you no longer can just look at the kind of topology of the, or it's much more difficult to look at the topology of the magnetic potential and identify all of the different structures that could be reconnecting. Right. Additionally, you can have kind of kinetic effects that come into play that alter the way that magnetic reconnection occurs within the turbulent medium. And so there was some recent results from the Magnetospheric Multiscale mission by Tai Fan and collaborators back in 2018 that was published in Nature. And so they were looking at the Earth's magnetosheath, which contains a plethora of turbulent fluctuations that generate lots of small scale current sheets. And they went through a couple of intervals of magnetosheath data, which I've kind of highlighted here in blue and red in this plot. And they looked at each of the small scale current sheets within the system to try and see if they could find evidence of magnetic reconnection going on. They ended up finding 16 examples of small scale reconnection events in these intervals. And in fact, one of the events had sort of oppositely directed electron outflows observed between the different spacecraft. So here, MMS 3 sees this positive electron jet, and MMS 1 sees this negative electron jet. So basically the two spacecraft crossed on either side of the X line and are seeing the two oppositely directed jets. Right, so this is kind of the smoking gun observation of ongoing magnetic reconnection at these small scale current sheets. But the interesting thing was that all of the reconnection events that were identified were occurring at small electron scale current sheets as opposed to ion scale current sheets, which we typically expect for magnetic reconnection. And they all had super alphanic electron outflows, and there was no clear evidence of any ion jets being formed. And this was kind of surprising because you would imagine that you could have no ion jets being formed if you were crossing inside of the ion diffusion region for the for the reconnection event. But you would expect that the kind of volume of space occupied by the diffusion region would be much smaller than the volume of space occupied by the ion reconnection jet if it was there. And so you would imagine if you're just sampling through a whole bunch of different reconnection events in a turbulent medium, you should be more likely to find the ion jets if they're there in the plasma. And so this led to the idea that maybe the ion jets just aren't forming at these small scale current sheets in the turbulent system. And this was kind of, has come to be known as electron-only magnetic reconnection. And so the idea of what's going on is that if you think about these kind of current sheets that are formed at the interfaces of these magnetic structures, typical size of these magnetic structures is going to be quantified by the correlation length of the turbulence, right? And so if the correlation length, and thus the length of the current sheets that are formed within the turbulent system is comparable to the ion scales in the plasma, then the ions won't have kind of sufficient space to couple into the newly reconnected magnetic field lines before the field lines fully relax, right? And so the ion jets just won't ever form, right? And so kind of idealized laminar reconnection simulations have tried to look at this by kind of artificially setting the size of the current sheets that are formed along the outflow direction by altering the size of the simulation box. And what they end up finding is that as you reduce the size of the simulation box and the length of the current sheet, you begin to reduce the speed of the ion jets at around a length of 40 ion inertial lengths. And as you get down to 10 or fewer ion inertial lengths, there's virtually no ion jets that are being formed. So the idea is that in the magnetosheath, perhaps the correlation length of the turbulence is short enough that the current sheets are small and you're getting this electron-only mode of magnetic reconnection going on. And this potentially has implications for kind of the nature of the kinetic scale nonlinear interactions, as well as potentially how the energy that's dissipated by the turbulence through magnetic reconnection is partitioned between the different particle species. So it's not been necessarily proven, I don't think, but you might imagine that if the ions aren't coupling into these newly reconnected field lines, then perhaps only the electrons will be getting any kind of heating that's associated with this electron-only reconnection. And so in a little bit, I'll be talking a bit more about electron-only reconnection. Another way that turbulence and reconnection can interact is that large system scale magnetic reconnection events can actually act as a driver for turbulence, particularly within the magnetosphere, as well as potentially other environments as well. And so this can occur through a number of different mechanisms, either through the instability of the reconnection outflows themselves. So as you generate these fast jets of plasma, those can potentially destabilize, and you can end up with quite complex fluctuations inside of the outflows that can develop into turbulence. You can also have the reconnection jets interact with the surrounding environment to generate turbulent fluctuations. And so kind of a good example of both of these is near-Earth magnetotail reconnection. So in the Earth's magnetotail, as part of kind of the Dungy cycle, right, you get magnetic reconnection events, and these generate fast outflows. So you can end up with turbulence that's generated in the vicinity of the X line that's just associated with the instability of these outflows. And in addition, you have the reconnection outflow that's going back towards Earth can interact with the kind of nearly dipolar field near Earth. And as it kind of hits this kind of stable magnetic configuration near Earth, it's going to cause a rebounding, and this will generate vortices and eventually develop into a turbulent region that's usually called the bursty bulk flow breaking region. And so I, as well as some collaborators and other people, have looked at turbulence within this region, for example, with the Themis mission. And there's also been a series of really good events from the Magnetospheric Multiscale mission looking at the turbulence that's more in the vicinity of the reconnection X line in the tail. And if you're interested in, say, the kind of global scale dynamics of the magnetosphere as a whole, right, the kind of reconnection that's going on in these environments can potentially play a role in kind of mediating how energy is partitioned across different kind of energy channels moving through the magnetosphere. And in particular, kind of the turbulence that occurs in the breaking region can potentially radiate waves out that propagate towards the auroral region in the magnetosphere and generate alphanic aurora. Right, so as I mentioned, there's been a series of really interesting turbulence or reconnection-driven turbulence events in the magnetotail that have been observed by the Magnetospheric Multiscale mission. So here's just an example of one that was looked at by Bob Errigan in a series of papers starting in 2018 and continuing on through 2020, where you can see that there's actually multiple reconnection events here. So MMS crossed over a reconnection event here, where you can see these this kind of bipolar VX ion flow. So this is the earthward and anti-earthward ion reconnection jets that are observed by the turbulence. There's another reconnection jet observed here. And so you can see that the magnetotail is relatively quiet outside of these reconnection events. And as soon as you get kind of reconnection going on, you end up with these quite vigorous magnetic fluctuations and electric field fluctuations, as well as particle energization. And these have been associated with kind of turbulence within the reconnection outflows. Right, and one of the kind of interesting things that you can do with these magnetotail observations of turbulence is look in detail at the kind of processes that are leading to this particle energization. And the reason for this is that you have this big dropout in the density within these events. And this means that the Debye length of the plasma is relatively large and in fact comparable to the formation size of the MMS formation. And so you can get really high time resolution and really accurate measurements of the current as well as the electric field from the multi-spacecraft from using kind of the curlometer technique to compute the current. And get exceptionally high resolution measurements of J.E, which quantifies the exchange of energy between the electromagnetic fields and the particles. Right, and so doing this, Errigan et al. Has been able to kind of look at the sort of particle trapping and acceleration that's going on to cause these very energetic particles. And in fact, there's kind of non-thermal power law tails to the particle distributions that are associated with this kind of trapping of particles within these turbulent fluctuations and acceleration. The last kind of way that turbulence and reconnection can interact, and I'm going to briefly mention, is that turbulence can also kind of perturb the sort of large-scale reconnection events that are going on in a system. So, for example, on the Earth's magnetopause, the magnetosheath is filled with turbulent fluctuations, and these are going to act to perturb the magnetopause, either causing indentations on the magnetopause or potentially altering the kind of shear angle between the magnetic field at different locations on the magnetopause, right? And this can potentially act to, help initiate magnetic reconnection of the magnetopause, or potentially lead to kind of patchy sort of localized reconnection events. And so I think this is a relatively difficult thing to explore with observations, just because, right, it requires kind of this large scale picture of what the magnetopause is doing. However, there's been some recent simulations by Li Chen looking at some aspects of this in terms of how the turbulent fluctuations that are generated by the shock upstream of the bow shock kind of propagate in towards the magnetopause and alter and perturb it. And I think this is potentially an interesting area of study kind of going forward, perhaps utilizing different conjunctions between different missions to look at kind of what the large scale configuration of the magnetopause is and how the kind of small scale fluctuations may be impacting it. Okay, so the last thing I'm going to talk about is some of the most recent work that I've been doing, looking at a survey of this kind of turbulence-driven magnetic reconnection, in particular the electron-only reconnection that I talked about in the Earth's magnetosheath using the MMS mission, right? And so the kind of question that we wanted to look at was, do we see any evidence that the correlation length of the turbulence is influencing the properties of the magnetic reconnection events that are occurring? And so to do this, I identified 60 intervals of magnetosheath turbulence that were observed by the MMS mission at kind of at the high burst resolution, right? So these points here are just showing the location of all of the events that I identified. And so they're spread out across the dayside magnetosheath and into the flanks, right? The intervals that were selected were greater than roughly 3 minutes in length. So this corresponds to many correlation lengths, which is ideally what we want, because we want to be able to get as many kind of magnetic reconnection events within the turbulent interval as we can, as well as get kind of good statistics of the turbulence. We avoided intervals that had large scale inhomogeneities within across the entire interval. And we also verified that what's known as the Taylor hypothesis was valid, which allows us to convert kind of the timescales that are seen in the time series into spatial length scales, just using the kind of background advection velocity. And this allows us to kind of probe multiple different length scales by using the temporal measurements, as opposed to just getting effectively one length scale from the kind of tetrahedral formation. And allows us to estimate what the correlation length of the turbulent fluctuations actually is. Right, so we went through each of these intervals and quantified what the magnetic correlation length of the fluctuations was. So remember that this kind of correlation length gives you sort of the average size of the twisted up magnetic field structures within the turbulence. And so if you compute the correlation function of the magnetic field within a turbulent environment, you expect that that will kind of decay towards zero as you go to large separations between points, with the idea being if you sample 2 points inside of a single structure, those will be at least partially correlated with each other on average. Whereas if you sample 2 very disparate points that are in 2 different magnetic structures, right, then there isn't any reason that they should be correlated with each other on average. And so you'll have a net zero kind of correlation between those. And so the kind of characteristic scale that this correlation function decreases over gives you an estimate of the average size of the magnetic structures that are in the time series. Right, and so you can quantify this kind of correlation length by either integrating this correlation function, or you can use say the kind of e-folding time, or do a fit to an exponential. There are various ways that people use to estimate this, but all of them tend to give roughly the same answer, at least for the intervals that I was looking at. Right, and so if you look at what the correlation length of all of these fluctuations was, you find that there's a kind of systematic variation of the correlation length within the magnetosheath across the as you go from the subsolar point into the flanks. So in these 2 plots are just 2 different ways of looking at that, either plotting the different correlation lengths as a function of location in the XY plane, or looking at the angle from the subsolar point. And either way, you see that there's this kind of trend of going from short correlation lengths near the subsolar point to longer correlation lengths in the flanks. And there could be various reasons for that, either the kind of evolution of the turbulent fluctuations, or kind of different processing at different locations in the shock. However, either way, the kind of interesting thing in terms of looking at magnetic reconnection in these intervals is that the actual values of the correlation length vary from around 10 ion inertial lengths to several tens of ion inertial lengths, which is right in this region where you expect the transition from ion-coupled magnetic reconnection events into the electron-only reconnection events. Right, and so then went through each of these intervals and systematically looked for magnetic reconnection events. I did this using a kind of partially automated algorithm. So we went through each interval and identified all of the intense current structures that were over a given amplitude. And there was kind of an algorithm for bunching together local maxima in the current into unique structures. We then went through each of those structures and rotated each of them into a local coordinate system of the current sheet. So in that kind of local LMN coordinate system, the n direction would be the normal to the current sheet. The m direction would be the guide field direction. And then if reconnection was going on, then the L direction would be the outflow direction. And then we checked each of the events that we had for if there was a reversal in the BL component of the magnetic field, right? As well as if there was a perturbation to the electron flow that was over a given threshold amplitude inside of that current sheet. Right, and the reason we looked at the electron flow as opposed to ion flow is that if electron-only reconnection is going on, then you would expect there to be electron jets, and you would also expect those in ion-coupled reconnection, whereas the ion jets wouldn't be there in electron-only reconnection. And then we went through all of the candidate events that were found by that procedure manually and verified if they actually looked like reconnection events. The kind of automated procedure wasn't very intelligent, right? So it tended to give lots of false positives, but it also tended to kind of over-select events. So you could trim it down to the ones that actually look like reconnection events. So doing that, we found 263 reconnection events out of roughly 2,500 intense current structures. So you have about kind of a 10 to 15% occurrence rate of reconnection at these current sheets. Most of the events didn't have any clear evidence of ion outflows. So this might be consistent with electron-only reconnection going on. Right, so here's just an example of what one of those events looks like. So you can see that there's this reversal in the BL component. You have this perturbation to the electron flow, which is the electron jet. Right, and if you look at where that electron jet is located, it's slightly shifted towards the side of the current sheet that has a positive BL, right? And this is consistent with the fact that if you have a guide field in the reconnection event, then there's going to be a J cross B force on the electron jet that will deflect it towards one side of the current sheet. And it's on the correct side for what you would expect for this event. You can also see this kind of negative to positive bipolar variation in the guide field direction, which is consistent with the Hall field that you would expect. There isn't a very clear signature of an ion jet. And you also have this strong J dot E within the event. So conversion from the magnetic field into the particles, which is what you would expect for magnetic reconnection, where you're transferring energy stored in the magnetic field into particles. There's also a smaller subset of events where we find evidence of ion jets being formed. There are roughly 18 of these, I believe. And so in order to verify ion jets, we looked at the correlation between the BL magnetic field and the perturbation to the ion flow in the L direction. And you're looking for a reversal in the correlation between the outflow and the magnetic field. So that's shown in this panel where in black, you have the BL profile. In blue is the ion jet profile, kind of referenced to where the BL profile reverses. And then in green is just a scaled up version of that. So that's similar amplitude to the magnetic field profile. And so you can see that right at the location where the field reverses direction for all of the spacecraft, you have this change in the correlation between the velocity and magnetic field profile. So it's consistent with what you would expect for an ion jet. And we have examples in the data set of both kind of partially coupled ion jets. So similar to this event where the actual amplitude of the ion jet perturbation is much lower than the magnetic field perturbation, as well as what I would call kind of fully coupled ion jets, where you have kind of an fully alphanic ion jet being formed. And there's also some instances where you see kind of this event has similar profiles for all 4 of the spacecraft, but there's some where you can see differences in the jet profiles between the different spacecraft, which is quite interesting. Also in this event, you happen to have a kind of small perturbation to the electron temperature that can be seen inside of the current sheet. So this may be a signature of electron heating going on. However, it seems to be relatively rare to be able to actually clearly see the electron heating profile in these events. So then we can look at kind of the properties of these reconnection events, and in particular, the thickness of the current sheets and the speed of the ion and electron jets, which are kind of the key parameters for looking at if it could potentially be electron-only reconnection. So if you plot the thickness of the current sheet that was observed versus kind of the peak jet speed that you see, there's kind of a correlation between the electron jet speeds and the thickness of the current sheet. So you tend to have faster electron jets at the thinner sub-proton scale current sheets, which may be consistent with electron-only reconnection. And then if you look at which current sheets have clear evidence of ion jets, you find that they tend to be the ion scale current sheets that you can clearly see ion jets within, whereas the kind of sub-proton scale current sheets don't have clear evidence of ion jets, which again is potentially consistent with what you would expect for electron-only reconnection. And then finally, we can look at how each of these vary with the correlation length for the intervals that we find. So note that the correlation length for each interval is kind of an average quantity. So you don't necessarily expect a one-to-one correlation between any given reconnection event in the correlation length, but you would expect potentially a change in the distribution of the kind of thicknesses and speeds of the jets as a function of the correlation length. And so if you kind of look at the relationship between the correlation length and the current sheet thickness, you find that larger correlation lengths tend to have kind of current sheet thicknesses that are roughly centered on the ion inertial length, like you would expect. And there seems to be this kind of slight downturn to shift of the distribution to smaller scale current sheets as you go to the smaller correlation length, starting at a few tens of DI, which is kind of consistent with where you would expect this transition to electron-only reconnection. And so you can look at kind of the cumulative distribution functions of current sheet thicknesses for different kind of bins in the correlation length. And here I've tried to mitigate the potential bias associated with kind of the finite resolution of the particle measurements. And you find that there is kind of a tendency for a shift in the distribution towards smaller scale current sheets for short correlation lengths as opposed to long correlation lengths. And it seems to be a statistically significant shift in the distribution. You can do the same thing with the electron jet speeds. And if you look at just the scatter plot, again, you see kind of this trend of the electron jet speeds being a bit smaller, closer to the Alfvén speed for the large correlation length intervals, and maybe a slight upturn at the small correlation lengths. However, when you do the same sort of cumulative distribution function, again, trying to mitigate potential bias associated with the finite time resolution, there doesn't seem to be as significant of a difference between the distributions. There might be a slight difference in kind of the tails of the distribution, but it's not clear that that's a statistically significant difference. And if you look at the ion jets, we have relatively few of them, so it's hard to look at the statistics. And it's not quite clear if there's any particular trend with the ion jets. But that could just be up to the fact that there's only a handful of these ion-coupled reconnection jets. So just to summarize, right, magnetic reconnection and turbulence have a very kind of complex and multifaceted interaction with each other that can be is potentially relevant for a number of different space plasma environments, such as the say solar corona, solar wind, Earth's magnetosphere, maybe even astrophysical environments. And the Magnetospheric Multiscale mission provides us with a particularly unique opportunity to look in detail at this interaction in a number of different ways observationally, both in terms of the driving of turbulence by magnetic reconnection events, as well as in terms of the reconnection events that are generated at small scale current sheets by the turbulence. And so in the work that I've been doing, we've been doing this kind of survey of turbulence-driven reconnection in the magnetosheath. And we find that small scale reconnection events appear to be a fairly common feature in the magnetosheath, occurring at roughly 10 to 15% of the intense current sheets. The majority of them don't have any clear evidence of ion jets, so they may be consistent with electron-only reconnection, and the electron-only reconnection may be more prevalent at in intervals with shorter correlation lengths, which tend to be near the subsolar point. So thank you for listening, and I'm happy to answer any questions.
Thanks, Julia. That was an excellent seminar. Yeah, so if anyone's got any questions, you can either raise your hand or put them in the chat. So I'll just wait a moment to see if anyone's got a question. While we wait, I've got a quick one, Julia.
Yep.
So on the 10 to 15% occurrence, did you look at any physical reason why those current sheets seem to prefer to have the reconnection versus ones that didn't? Or is it just an over-identification, or is there like a physical thing happening or a physical reason for that?
Yeah, I mean, I haven't looked in detail. I mean, you don't necessarily expect every current sheet to be actively reconnecting in any given environment, right? It could be that they previously reconnected and the configurations just changed, that it's not being driven anymore. It could also be that, right, I mentioned that in 3D, you can have quite complex magnetic configurations, right? And so there could be the kind of selection procedure that I've used has kind of targeted the ones that are more sheet-like, at least on the kind of length scale that you traverse the current sheet, right? And so it could be that there's kind of more complex magnetic topologies that are reconnecting that I'm not actually identifying.
Yeah, that you're not seeing.
It's quite a subtle point in terms of why the ones that we see are reconnecting versus other ones aren't.
Okay.
Some could be, and just we haven't found the more complicated types of reconnection.
Okay, yeah, so Martin's got a question in the chat. Do the correlation times of turbulence fluctuations in various locations in the magnetosheath show similar trends to the correlation lengths you've shown, given that the flow speeds vary with position? So that's in the chat if you want to, if that
yeah, was... so yeah, I guess that it may, there may be a bit of a relationship between the flow speeds in the correlation lengths. I guess, right, you use the flow speed to estimate the correlation length, so there's going to be a correlation kind of implicit in that, in a way. So I wouldn't be surprised if there is. I haven't looked in detail though.
Okay. Has anyone got any other questions? If not, I might ask another one. So you were saying about if they are like the 3D current sheets and structures, would say a simulation be able to help with identifying those sort of intervals better, if that makes sense?
Yeah, potentially. I mean, directly simulating kind of any given turbulent environment, like a one-to-one simulation, you aren't going to be able to do, right? Because, yeah. But certainly there's been quite a bit of work recently trying to look at how to best identify magnetic reconnection events in general within a turbulent environment. And I know Jefferson at MSSL has been working on some things like that and looking at different parameters and which ones can be used to identify reconnection events. But it's a very non-trivial problem. Even in simulations, it's very difficult to figure out which kind of 3D current sheet is reconnecting and which are not.
Yeah.
So it's definitely an active area of research. I know there are people looking at ways to use kind of machine learning to try to identify reconnection events within turbulent simulations and stuff like that. So maybe one day that could be implemented in observations as well. But I think, as kind of a first stab at it in the observations, I think focusing on the ones that are kind of most sheet-like and look like the kind of traditional reconnection events that we expect is certainly a good first step.
Yeah, I was just thinking, because now you've got like a catalog of events that you've sort of identified almost by eye, but like, so you're using some algorithm, but you could then probably use that as a training set for an algorithm.
Yeah, certainly. I think there are
that then test against. So yeah,
to adapt this into kind of a more machine learning sort of algorithm potentially, because right, there's lots of knobs you can mess with in the algorithm.
Yeah.
So you can use machine learning to try to set what the optimal knobs are.
Yeah. Okay. Has anyone got any other questions? If not,
there's one in the chat.
Is there another one in the chat? Okay. Yeah, sorry, I had the chat open, so I didn't get the notification up. Yeah, so Oliver's asked, can you please explain which measurements in particular the Taylor hypothesis allows you to make? Are there any circumstances where the Taylor hypothesis doesn't hold in your experience with this or other studies?
Yeah, so the Taylor hypothesis for this study in particular was used in order to estimate the correlation length of the turbulence, right? So in reality, I've plotted it here as a function of length scale, but in reality, this is a temporal correlation function, right? And then you can use the Taylor hypothesis to convert that into a spatial correlation and estimate what the correlation length is. And so the reason that you need to use the Taylor hypothesis to do that is because to compute the correlation function, you need to have different points at lots of different length scales within the plasma. So with MMS with 4 points in a tetrahedral formation, you kind of only get one spatial separation. So you need to be able to get lots of spatial separations to estimate the correlation length. So that's where the Taylor hypothesis comes in here. Certainly in the magnetosheath, not all of the intervals seem to have the Taylor hypothesis doesn't seem to be valid for all of the intervals in the magnetosheath for sure, which isn't unexpected given that you tend to have kind of slower flow speeds relative to say the solar wind. But all of the ones that I used in this study, the Taylor hypothesis did seem to be valid. And the way that we looked at that, extra slides, right, is that you can directly compare the kind of some sort of turbulence statistic estimated with the Taylor hypothesis to the multi-spacecraft statistic at the particular scale that you have multi-spacecraft separation, right? And look at how those relate to each other and see if they agree with each other, particularly along the flow direction, right? So in this case, the way I did it for the intervals I looked at was look at the second order structure function. You can compare the ratio of the second order structure function estimated from the Taylor hypothesis to the multi-spacecraft separation, and then look at that as a function of angle relative to the magnetic field. And you would expect along the flow direction that they would agree with each other. And because there's a possibility of having anisotropy to the turbulence, you can potentially have a variation as a function of angle. Right, and so for the intervals that I looked at, they agree very well along the flow direction. But in general, that's not always true. So it's certainly something you need to look at when you're dealing with kind of either single spacecraft measurements or kind of measurements such as this, where you've kind of got access to one length scale with multi-spacecraft measurements, but not multiple length scales. I don't know if that fully answers everything you were interested in, but.
Yeah, I think Oliver said brilliant, thanks in the chat. So we've got one more question from Richard Mace, who says, in general, MHD turbulence requires a resistive MHD model, yet in space plasmas are largely conditionless. What is the source of resistivity that gives rise to MHD turbulence that you observe? And great talk, by the way.
Yeah, so I mean, of course, in general, we don't really have resistivity in collisionless plasmas. So I guess the way to think about it is that it's not really resistivity, but there's kind of an effective dissipation that occurs through the kind of ensemble of different collisionless plasma processes that can exchange energy from the fluctuations into the kind of thermal or second moment of the particles, right? So that's effectively what the resistivity is in a collisionless plasma. It's all of your kind of wave particle interactions or instabilities that allow you to exchange energy from the fluctuations into the particles. There's certainly a very valid and open question in terms of understanding how you get kind of irreversible dissipation from that, right? But in a way, you can imagine that, if you have enough of these processes going on in a complicated environment, right, the chances of you reversing all of the steps that you did to scatter the particles around in the distribution function becomes less likely. So maybe you get an effective kind of irreversibility from that. But certainly that's a very open question in terms of understanding, how you get irreversible dissipation in a collisionless plasma. And one step in understanding that is trying to understand which of the different processes that can operate in collisionless plasmas are most important for dissipating the energy in the turbulent fluctuations.
Yeah, so Richard's put, yeah, so non-collisional plasma instabilities, ways, etc., and then says thanks. So that answered it. Okay, what's the time? Probably got time for a one quick question if anyone's got one. Okay, if no one's got another question, then I'd like to thank Julia again for an excellent seminar. And I guess that's, yeah, no worries. And then we'll let people go and enjoy lunch in the sun. Hopefully it's sunny where you all are. Certainly is here in London. Yeah, thanks everyone for coming. Thanks for the good discussion at the end as well. And thanks to Julia again for the great seminar. Thanks everyone.